Good day, everyone. Okay, so today we're going to start lecture 6. It's on data acquisition and management for lifecycle inventory analysis. Okay. So our learning objectives for today include the following: understanding LCI data requirements, creating and assessing the data quality requirements for a study, recognizing appropriate data sources for LCA, mapping information from LCI data modules into unit process framework, extracting data and metadata from LCI data modules and using them in product system analysis, and then generating inventory result from LCI data sources and performing interpretation analysis on LCI results. Okay, so before we proceed, one important thing to note is always document everything, especially your assumptions, no? And guidelines on this can be seen on ISO 14041 document, okay, specifically section 8. Okay, and again, I'd like to remind everyone that when you're presenting your quantitative solutions, first, always describe the method and the data. Second, of course, you present the results. And then third, discuss what is relevant or interesting about the results. Okay, and I mentioned last time that there are 3 main approaches in doing LCA. One is process-based, the other one is environmental input-output, and then the third one is hybrid approach. And the focus of this course is the process-based approach. And we're going to, the things that we're going to discuss in the succeeding slides are focused on process-based, although of course, discussions on data quality requirements are also applicable to the other 2 approaches. Okay, and before we proceed, let's just recall the following definitions. First, elementary flows. These are material or energy entering or leaving the system, and they directly come from or to the environment, and they don't undergo any human transformation. Okay. And unit process. Okay, so this is the smallest portion of a product being studied for which LCI data is available. And then you have your inputs or outputs. Okay, of course, these are the materials or energy entering or leaving a unit process. And then you have your system boundary, okay, which basically shows you what is inside or outside the system of analysis. Okay, now after you establish the scope and the goal of your study, how do you proceed? Okay, so say for example, this is the scope of the study, okay, from cradle to grave, basically, and if we include recycling, cradle to cradle. All right. Okay, so you have your goal and scope. Now, what you see here is a flow chart, okay, showing the procedures for inventory analysis. And this was adapted from ISO 14044 2006. Okay. You can see here the overview of the different steps. So, of course, first you have your goal and scope. And then after that, you have to prepare for data collection. And one of the outputs for preparing for data collection is a data collection sheet. Okay, and then proceed to data collection. Output is, of course, a collected data, but you have to validate the data. Okay, and when you have the validated data, you can proceed to relating the data to the unit processes. And if after that, you have to validate the data per unit process. Okay, and after doing that, you then relate the data, the validated data per unit process, to the functional unit. Okay, and of course, at that level, you also have to validate again. And then after that, you have data aggregation. And from the data aggregation, you have the calculated inventory. And then after that, if there is a need, then you can refine the system boundary. And of course, you have your completed inventory. Here, you can see here an alternate route if there is any allocation, okay, that is needed. And if you have to include reuse and recycling, and then you have to, before you relate the data to the unit process, you have to take that into consideration. And then if you have to refine the system boundary or make any changes in terms of the scope of your analysis, you also have to revise your data collection sheet and proceed again through the different steps. Okay. Now, these are the steps in performing a life cycle inventory analysis. Okay, as we have seen the overview. Okay, this slide just shows some details for each of the steps that I just mentioned. So, for example, for preparation of data collection, okay, which is of course based on the goal and scope, you can use a process flow diagram. Okay, and of course, you have to remember your system boundary in creating your process flow diagram. And then another thing that can help you with this is your SIPOC diagram. Okay, for data collection could be via on-site visits, could be through surveys, it could be through published scholarly works, so obtaining data from published scholarly work. Okay, or maybe an estimation model that you have developed yourself, and then maybe from databases as well. Okay, so these are just the rest of the steps in performing an LCI based on ISO. Okay. Again, just a note on data validation. You have to perform this even when you're just reusing someone else's data, even if that is that data comes from a journal article, for example, that has already been peer reviewed. And of course, you have to determine whether there is a need for data allocation. Okay, so let's go through each step in more detail. So the first step, as I mentioned, is preparation for data collection based on goal and scope. Okay, so of course, again, recall your goal and scope. Okay, your product system boundary, and of course, your system boundary. Now, for every unit process within the boundary, you have to collect data that represents the transformation of the inputs to outputs. So you can use, of course, diagrams like this. You have your unit process, and then you have your inputs, you have your outputs, okay, including your product, your emissions, and then you also have inputs from nature. So this one is from Technosphere. Of course, this can be rearranged now, but the general illustration of a system, okay, or a unit process can be as such. So as I mentioned, drawing a process flow diagram, okay, will help you identify the unit processes and their interrelationships. So this is an example of a process flow diagram for gold jewelry manufacturing system that I and Dr. Soriano created for gold jewelry manufacturing in Bulacan. Okay, so you can see here the different processes, the outputs from different processes, etc. Okay. And after knowing the flow, okay, of the unit processes, okay, you can now clearly map out the inputs and outputs for each unit process. Okay, so the inputs and outputs could include, the inputs could include raw materials and energy. For outputs, you have waste or co-products. So you have atmospheric emissions, waterborne waste, solid waste, other releases, and co-products. And recall, this is the supplier input, process, output, customer diagram. Okay. So after you determine the flow and interrelationships of the different unit processes and identify the inputs and outputs, okay, for each unit process, you can, well, before you proceed to actual data collection, you should have your data collection sheet already, okay, before you go there. You go to the site, for example, or before you start scourging the net for sources. And so on, okay, so that your data collection process is more organized. Okay. All right, so we're done with these two. Let's now, as I mentioned, you have to have your data collection sheet. Okay, so let's now move on to data collection. Okay, step 2. So you can either measure, calculate, or estimate or source from reliable data sources. But again, the gold standard is for you to collect your own data. Okay, and primary data is directly measured, okay, inputs and outputs of the processes, okay, on the site or for the specific machinery or transformation that occurs. Okay, you have to have a reasonable representation of the process, okay, and to have this, you have to have proper design of experiment and proper sampling, okay, and you have to be able to provide a clear data collection summary. Okay, and this could include descriptive statistics such as the mean, the median, standard deviation, and other relevant statistical properties for your measurements. Okay, now here is an overview of some data needs. So let's start with the first bullet. Know what you are tracking for your inventory. Okay, so it can get really confusing at some point if you're handling so many data from so many sources. Okay, so you have to make sure to track everything. Okay, also specify your inventory scope. Okay, so you have to choose specific emissions. For example, you can't just say air emissions or water emissions. You have to be more specific. So specific emissions of gases, for example, or substances. So for example, carbon dioxide or sulfur dioxide, okay? And to identify these specific substances, you can use your desired impact categories as guides. So for example, if you want to focus on fuel use or if you want to focus on climate change, etc. Okay. Going back to overview of data needs, the second bullet is for you to be able to identify data for all the inputs and outputs, okay? So from ISO 14044 on elementary products and flows, okay? So you have energy inputs, raw material inputs, ancillary inputs, other physical inputs. And then you can also have products, co-products, and waste, releases to air, water, and soil, and other environmental aspects such as noise, odor, land, resource depletion, etc. Okay. And then you have to be able to clearly characterize the level of detail or aggregation of your data. And this may depend on the purpose of your study, the availability of data, as well as the amount of uncertainty or variability that is involved in your data. Okay. Next, you have to be able to follow the data quality requirements that you have specified from the outset. Okay. And then, okay, before we proceed to the last bullet, okay. So again, remember there are primarily two types of data. You have primary data and you have your secondary data. So primary data is one that is collected for the specific project of interest, okay? And secondary data could be from LCI databases, okay, or averages from industry, okay, or industry level data that are available, okay. So the gold standard is primary data. And the suggestion is for you to be able to directly measure inputs and outputs if feasible. Okay, so for example, if you want to look at energy use of a process in an automobile assembly line that fastens a component onto the vehicle with a screw, okay, what you can do is to attach an electricity meter to the piece of machinery that attaches the screw. Okay, or if you want to quantify fuel or material used in an injection molding process, what you can do is measure the workpiece or fuel or other materials as they enter the machine. If you want to quantify, for example, emissions, then you can place a sensor near the exhaust stack. Okay. Next pointer is that you have to use statistically sound experimental design. So you have to be able to use proper statistical sampling when collecting the data so as to arrive at statistically sound results. Okay, that means that you will be able to avoid biased results. Okay, and of course, you have to be able to report the measures of central tendencies and the spread of the data. So the mean, the median, standard deviation. Okay. And characterize the probability distribution function of the data if possible. All right. Now, there are some pitfalls of primary data, although it is the gold standard. No, one, the data is only as good as the measurement device and, of course, the measurement technique. Okay, and the people measuring if there are people involved. So, and of course, when you outsource measurement, okay, verification and validation may involve issues with translation or misalignment in expectations and results. Okay, so I mentioned earlier data quality requirements. You have to be able to follow data quality requirements. Okay, and these are these data quality requirements are things that you set from the outset. Okay, so there are 10 things that you could take into consideration per ISO 14044 from this section 4.2.3.6. Okay, you have time-related coverage, okay, which is basically the age of the data and the minimum length of time over which the data should be collected. You have geographical coverage, okay, the geographical area for which the data for a unit process should be collected to satisfy the goal of the study. And then you have technology coverage, okay, the specific technology or technology mix. You have precision, okay, the measure of the variability of the data for each data expressed. Okay, so for example, the variance. And then you have completeness, okay, or the percentage of flow that is measured or estimated. Okay, this is usually mentioned as a cutoff criterion. And then you have representativeness or the qualitative assessment of the degree to which the data set reflects the true population of interest. Okay. And then consistency. Consistency is a qualitative assessment of whether the data or whether the study methodology is applied uniformly to the various components of the analysis. Reproducibility is, of course, whether future researchers will be able to perform, okay, the study that you conducted. And then sources of the data, you have to be able to clearly summarize all the sources of your data and, of course, provide an assessment as to the soundness of these sources. And then the uncertainty of the information. So discussion on some uncertainty related to the information that you have. Okay, an example of data quality requirements that you can set from the outset. Okay, say for example, you're looking at an LCA of Christmas trees, no? You see here data quality category. You can have temporal, geospatial, technological, and then some requirements that you deem from the outset are reasonable for the data that you have to collect. Could include data within 10 years of study for temporal. For geospatial, data matches location production. Technological, most common production process basis. Okay, so what would be the data quality indicator for each of these categories? Okay, so for example, temporal. Okay, for artificial trees, it could come from a 2009 data. Okay, and say for example, you're conducting a study in 2010, okay, and your data is from 2009, then that's still acceptable given your requirement. Natural trees, 2002 to 2009 data, okay, and so on. All right, you can find this actually in the LCA book. In terms of temporal coverage, some questions that you might want to ask are the following. 1, what is my year of analysis? 2, has the process changed recently? 3, is it likely to change in the near future? Have upstream or downstream processes changed? Okay, has new information arisen recently, and from what year is the data? Okay, because sometimes if you look at journal articles, the results or the year that the article was published is not necessarily the year in which the data was collected. Okay. Next, we talk about geographical location. Okay, so you have to take into consideration the geographical scope of your study. Oh, by the way, I took this from Google Maps, and I noticed that they actually label this as the South China Sea. Okay, so I put here West Philippine Sea instead. Okay, so geographic coverage. Some questions that might be helpful for you. Are you looking for a specific location or a general region? Okay, why does geography matter, for example? Okay, so let's look at this example. This is a map from a study that I and my advisors did or published, okay, on environmental science and technology. Okay, sorry, I forgot the journal momentarily. The title of the study was Regional Variability and Uncertainty of Electric Vehicle Life Cycle CO2 Emissions Across the United States. Okay, so you can see in this map different colors. Okay, the colors actually indicate the probability that a Nissan Leaf, which is an battery electric vehicle, okay, the Nissan Leaf emits less CO2 than a Toyota Prius, okay? And this is the case being investigated here. Delayed charging, consumption-based marginal grid emissions. Yun yung assumptions that were used here. Okay, so you can see if it's very green, it's 100%. If it's red, then it's 0. Okay, and as you can see in different places in the US, okay, there are different levels of probability that a battery electric vehicle, specifically the Nissan Leaf, actually emits less CO2 than a Toyota Prius, which is the most efficient non-electric vehicle, okay, that was considered in this study, okay. So the geography could affect one, regional emission factors, okay, so for electricity, for example, the technology choice, okay, so most likely, for example, in the case of gold jewelry, okay, the technology employed in Bulacan would be different from technology employed somewhere else in the Middle East, okay. Operational requirements could also vary, transportation requirements as well, and therefore the potential emissions as well as the impact of those emissions. And of course, you have to be able to clearly identify the scope, the geographic scope for transparency reasons. Okay, and then again, you have to be able to state also the technology scope of your study. Okay, so there could be different pathways to the same product. Yes, I mentioned earlier the manufacturing of gold jewelry in the Philippines, specifically in Bulacan, might be different from that in countries in the Middle East. Okay, and the possible criteria could include specific company, specific technology or technologies, average technology mix, or representative technology. Okay. Now, on data sources, okay, again, related to data quality, you have to ask whether the data source is trustworthy. Is it peer-reviewed? What are the assumptions? Okay. What type of data were used in the source? Okay, were they measured? Were they estimated? Were they calculated? Were they aggregated? What can you say about the methods used in each of these? And then, if you are selecting multiple sources, why are you doing that? Okay, is it because not one source is available for all the different parameters that you're looking in your study? Okay. If you are using a source, okay, you have to be careful, okay, to look into their original source, because your sources might have used an estimation model for which they needed some data from other sources. So you have to check if those data sources are also reliable. Okay. Now, these are just common data driven mistakes. Okay. One, using the data that is inconsistent with the targeted processes. Okay. So these are mistakes that I would like you to avoid in your project. Okay. Second, developing internally inconsistent models. Okay. Third, treating missing data as zero. Fourth, treating highly uncertain data as zero. And fifth, treating analytical detection limits as detections. Okay. In terms of data sources, okay, you can have several. So again, you can have primary data. You can have LCI databases. So these are some of the popular LCA databases and most comprehensive so far. So of course, you have the EcoInvent, okay, which is used by CIMA Pro. The approximate cost is $3,000 US. I think these values are actually not updated. You can look it up on your own, no? But years ago, this was the price, okay? The number of processes that are included in EcoInvent, 4,000 plus. Of course, this could be higher now. However, although it has data from around the world, okay, majority is from Europe, okay? And it is available directly or embedded within LCA software. Available directly meaning you can just purchase the EcoInvent itself. And then you have the US NREL Lifecycle Inventory Database. Okay, this is free for companies. Okay, but if you have to publish, you have to pay. Okay, so 600 plus number of processes. Okay, it is US focused. Okay, and it is now hosted by the USDA LCA Digital Commons. And you can also search for the USDA LCA Digital Commons. Okay, they have 300 plus number of processes. It is focused on agricultural products and processes. Okay, and it is geospatially specific for the US. And then you have two other free databases here, ELCD and then BES. Okay, there are 300 plus for ELCD. Okay, they have relatively few processes. Okay, and they are spread across various sectors. But there are additional data being added. And for BES, they are focused on building and construction materials. And then you have GABI. Okay, it is worth 3,000 USD. Maybe this is higher now. It has more than 5,000 processes. The database was made by PE International. They have some global data, but again, heavily focused on European data. Okay, so this is an example from NREL LCI database. Okay, so you can see here the different unit processes, okay, and some description. But if you explore their data, their website further, you will see that they have a very good documentation process. And for each of the unit processes, there's a very good set of metadata available. This is for CIMA Pro, okay? So you can look at the different processes, the different materials, energy, etc. Okay, so you can have either processes or product stages or waste types, okay, etc. Okay, so if you say click on one of these, oh, okay, there was supposed to be a slide, another slide that shows the metadata for each of these items. Okay. Please remember that the data sources is the heart of tools, okay? So all tools such as the CIMA Pro or the GABI are just front ends to the databases, okay? And these softwares, they aggregate and calculate the inventories and of course, perform impact assessment. But the data is the important part, okay? The interface is there, to help you, of course, visualize, organize information, present results, etc. Okay, but you have to examine the data documentation and the data to get what you actually need. Okay, so this is the one that I was looking for. So this is the one for CIMA Pro. I skipped a bit, I guess. So you can see here the documentation for each unit process. Okay, you have the time period, geography, technology, etc. And more information about the data set. All right. Now, what can you get from tools such as CIMA Pro? You can get key inputs or outputs, unit process emissions and other inventory data, life cycle emissions and other inventory data, the data sources, and of course, documentation of the data, and then impact assessment. I have to make a point that not all data are measured even from CIMA Pro, okay? So you have to be careful, okay? And then another data source is government sources, okay? So for example, in the US, you can get data on energy from the US Energy Information Administration. Okay, in the Philippines, you could probably get information from Department of Energy as well. Some data that you might need could also come from the PSA. And then you have industry reports. Okay, so in previous sessions, we talked about the industry report on LCA of bottled beverages, for example. And then you have, of course, academic literature. Okay, so academic literature is an important source of LCA information. There you can find complete inventories. You can also find inventories from unit processes, okay, which doesn't necessarily have to be applied in the same context that context meaning like a product system, okay, that was used in the study. Okay, so you can just extract information for a specific unit process and use it in your study if it is relevant. And then there's also reporting of primary data, okay, that is not available elsewhere. Okay, so maybe there are studies that specifically focused on obtaining primary data for some processes that you might need in your study. Okay, estimation of difficult parameters, and then you can also see how similar studies were scoped out, which can then help you in deciding how you will scope out your study as well. Okay, and you can of course find this using databases. Okay, so if you look at the metadata, you can probably find the sources there. Okay, and some of the sources could be from literature, or you can just directly search through Google Scholar or Web of Science, etc. And then of course you can come up with your estimation techniques. Okay, now of course, data collection is not necessarily primary data collection, okay? In fact, it is rare that LCA relies on pure primary data, okay? They usually have to use at least some secondary sources. And some studies are actually 100% based on secondary sources. And this is because it really takes time, and data collection is the most laborious part of life cycle analysis. Okay, so let's look at this example. This is a summary of data sources by life cycle stage from the LCA work that I and my advisors did on electric vehicles. So you can see here the different life cycle stages, okay, the method and source, okay, and then the value or the distribution that was used. Okay, so as you can see here, the sources or the methods are varied. Okay, so you see here information from GRIT. Okay, GRIT is a model. Okay, and it comes with the software. Okay, that was developed by Argonne National Laboratory. Okay, it was sponsored by the U.S. Department of Energy, and you can actually download it. Okay, it's a life cycle model. Okay, it's very useful. So it's very useful, especially when you are dealing with transportation. Okay, so GREET stands for Greenhouse Gases, Regulated Emissions, and Energy Use in Technologies. Okay, going back. And then, as you can see, there are some academic literature as well, and some estimation techniques, okay? And here you can see the different values and the distributions used, okay? So I would like to see something like this for your project. Of course, as I mentioned earlier, before you even start collecting data, you should have your data collection sheet with you. So this is from ISO 14044, okay? Example of data sheet for unit processes, okay? Example of life cycle inventory analysis data collection sheet, etc. All right. So you have here the different emissions, units, quantity, and then the description of the sampling procedures used. Okay, so 3 steps checked. After data collection, what do you do? Validate the data. All right. So you have to be able to check energy and mass balances. Okay. Compare with secondary data from reputable source, okay, the data that you have, okay, and then include discussion on data validation in the main text or appendix. So for example, okay, you can include something like this. Collected data from the year 2012 on the technology-specific process used in this study was compared to secondary data on the similar injection molding process from 2005, and then you put the reference. The mean of the collected data was about 10% lower than the secondary data. This difference is not significant, and so the collected data is used as the basis for the process in the study. Or it could go something like this. Collected data, yada, 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 was compared to secondary data on the similar injection molding process from 2005, reference. The mean of collected data was about 50% lower than the secondary data. This difference is large and significant, but is attributed to the significant improvements in this industry since 2005, and so the collected data is still chosen as the basis for the process in the study. Okay, so you explain why there could be significant difference and whether or not you accept the data. And then again, emphasis on data validation. No? So after you collect the data, you should take a pause and assess, okay? Is the data meeting the data quality requirements that you have stated from the outset, okay? Are the data that you have, okay, within the range that are expected, okay? And then are the mass balances maintained, okay? Is it comparable to other processes? Okay. Is there a modification of the scope that is needed given your data collection experience so far? Okay. And of course, the results of this data validation process should go in your report. Again, a note on data collection. LCA is really very data intensive. The data you need may not even exist. That's why we've done some exercises on estimation techniques, okay? The data can come from various sources. So you have to be really able to track, okay, all your sources. And there is often a need to iterate as you go, okay? And of course, think before you use a data source. Okay, so after validation, the next step is data allocation. So let's look at this. It would be nice if, say, in the transportation process of if you're doing an LCA of tomatoes, no, it would look like this, no. The only product that is being transported is tomatoes. However, what if the transportation process looks something like this? Okay, you have to be able to take into account the other co-products of this transportation unit process. All right, so therefore the need for data allocation. So more on this later on in the course. Okay, the next step is relating the data to the unit process. Okay, This means that the scale, the various collected data into a representation of the output of the unit process. Okay, you have to be able to scale the various data that you collected into a representation of the output of the unit process. Okay, you have to be able to collect all of the inputs and outputs as needed for one unit output from the process. All right, so this is an example. Okay, so for example, the output is a plastic part in an injection molding unit process. Okay, and your raw LCI inventory would be this 1,000. Okay, 1,000 pounds. Okay, and these are the inputs and then other outputs. So inputs, virgin resin, water, energy. Okay, and these are the units of measurement. And you have your raw life cycle inventory. And then in addition to the plastic part, there's an output in terms of waste, solid waste to landfill in pounds, okay, which amounts to 16. All right. Now, the next step is relating the data to the functional unit. So first, you relate it to the unit process, right? Now, okay, you have to be able to relate it to the functional unit. Remember that you are doing an overall study on the basis of one functional unit of product output and not simply of one unit of all processes involved. Okay. So if we take, if we build on the previous example, okay, so this, we already discussed this part. So you have the raw LCI for the unit process, okay? So the next column is LCI flow per pound of part, okay? So for the third column, it's just the LCI, life cycle inventory flow per pound of part. So per part, so we divide this by 1,000. That's why you get 1. Also divide by 1,000 all the other values to get these values here. Now to relate to the functional unit, okay, you have to know, for example, the relationship with the functional unit of functional unit used in the study to this output here. So for example, that we assume that an empty plastic milk container has a mass of 2 ounces or 0.13 pounds, okay? Then this data has to be translated in terms of that amount, okay? So one output of plastic part is 0.13 pound in this example, okay? So because of that, you have to be able to multiply this, okay? So these values by 0.13, okay? Okay, so let's build on the injection molding example. So say the reason you are interested in an injection molding unit process is because you are studying the life cycle of milk with a functional unit of 1 gallon of milk, which is assumed to require milk, molded plastic packaging, and adhesive labels. You would then collect data for each of the components of the packaged milk. If the empty plastic milk container has a mass of 0.13 pounds, then the accepted data in the previous slide could be used by scaling all the per pound values by 0.13. Okay, and this is shown in column 4 here. And of course, you have to validate this. Next step is data aggregation. So in the previous step, okay, you already have all your data in terms of the functional unit. So then you can just add up the data in this step, which is data aggregation. So for example, this is a table from an LCA on energy to make wool. Okay, so you have the different life cycle stages per functional unit, in this case, a ton of wood. Okay, so you now have gigajoules for farm, for processing, for transportation per ton of wool. Okay. Now let's proceed to an example, okay, a more complex example, which is, and complete example, which is on online music, no? And this will help us practice on functional unit, allocation, and other issues. So the case here is that Matthews and company were approached by a large software company to study the energy and CO2 impacts of downloading music. Now the goal, the goal is to compare CO2 impacts of different methods of delivering music to consumers. And this is CDs versus downloads, okay? There is an additional distinction for CDs. You can either buy, at retail store or buy it online. Okay. Now there are some considerations. One, the goal and scope have already been identified. Which is basically to compare download versus CD as music delivery method. Next, functional unit. What should it be? Some considerations would include, is a downloaded album the same as physical one? Obviously, they are different. Two, do people buy whole albums online or just single songs? So what are our options for functional unit? You have to think about the whole life cycle. And in this case, Matthews and company used one album of music as the functional unit. In terms of the system boundary, what should be included? So we can draw first system diagrams. So this is for the first case, the process flow diagram for CD retail. So you can see here from recording, CD production, and concurrently you have the visual artist designing the liner printing, and then the outputs from this go into CD printing. And of course, we also need the jewel case and the plastic wrap for the CD, and then packaging before it goes to warehousing, and then retailing, and the use of the CD, and of course, disposal. Now, for process flow for CD bought online, there is an added unit process here, which is home CPU use for ordering. And then you have the process flow diagram for downloaded music. So you have still recording, you still have the visual artist, but the other materials are not included anymore. The output go directly to the digital music server. And then, of course, you still have your home CPU use for ordering. And then you have use and disposal or for burning. Now, question, did Matthews and company use an appropriate functional unit? So, oops. So some assumptions include after burning digital album on the CD, the product should be functionally equivalent. So that means that you can use in either digital or CD format. Now, because of this, you can then ignore production of laptop, CD player, and iPod, etc. The sound quality may not be similar to some customers though, but for most, do they really care? Now, in practice, they are probably used differently. So the digital downloads could be used more in computers and digital music players, while the CDs are used more in cars, CD decks, etc. So you just include this in your discussion. Some assumptions and data on the that were used in the study. For CD and packaging production, data were obtained from reports, from EcoInvent, and from IOLCA. So we will discuss this briefly later on. For cardboard packaging for retail or e-tail, this was obtained from EPA WARM. This is actually another good here. It's another good tool, for studies relating to solid waste. And then you have EDF paper calculator. So this is another good tool again. So you might want to explore these things. And then for distances and delivery energy, this data came from logistics companies, from GRIT, and from previous work of the authors. Okay, there's a note here that there are very large ranges, okay, in terms of the data that were obtained. And then for warehouse and retail store energy use, the authors used government sources and previous work. And then for home CPU use for ordering, there was an assumed range, and then they used energy star data. Okay. Now for internet backbone energy use, okay, information came from Taylor and Kumi, assuming 60 to 100 MB album size. Okay, and this was the data. No, in 2000, this was the electricity intensity per gigabyte. Okay, but by 2006 to 2008, okay, you can see the very significant decrease. Okay, very significant decrease in and electricity in this intensity. Okay, why do you think is this changing so quickly? Okay, in this case, no, it is important to use the most recent information on electricity in this intensity. Okay. Next, on customer transport. Okay, so customer transport usually accounts for significant impacts based on previous studies. Okay, and it is usually difficult to model given a large variation in fuel economy, distance, vehicle utilization, etc. Okay, now in this study, okay, they use this simple equation. Okay, this model simulates distance, okay, fuel economy, passengers per vehicle, and purchased items per person using realistic ranges. Okay, the assumed correlation between distance and items or person per trip and distance and retail or distance for retail delivery were also included in the write-up. Okay, now let's move on to the results. Okay, so for the results, okay, this is a graph of the cumulative energy demand per album. Okay, so on the x-axis you have the different cases, and then on the y-axis you have the megajoules primary energy. Okay, and the different parts of the bars, okay, are labeled as such. Okay, so this is the legend. And as you can see, for retail, for example, the item, okay, that uses the highest amount of energy is customer transport. Okay, but for those that need case production, okay, case production also accounts for a huge portion, no, of the energy use. Okay, so let's look at CO2 emissions. Okay, it's very similar, so the profile is very similar. So let's look at the summary statistics. Okay, so for CD or packaging production, it's about 32 to 69% of total. All right. For customer transport and last mile, okay, it's 52% of retail, 24 to 28% of e-tail. And then you have other significant contributors, including warehousing, retail store, and individual cardboard packaging. Okay, while for upstream internet usage, it's actually as important as CD or CDR production. So let's go back, no? Okay. So this is CDK's production. And if you look at data center energy, okay, it's almost as big as the CD production itself. Okay, bigger than CD production, almost as big as CDK's production. Okay. So again, transportation really accounts for a big part of the energy use as well as the CO2 emissions. Okay. Now, on uncertainty and variability of the data that were used, the authors looked at the rank correlation importance, okay, for the different parameters, and it shows that shows the variables contribution to the uncertainty of or variability of the results of the study. And you can see here data for data centers, for example, have high contribution in terms of uncertainty or variability. Driving distance, of course, and so on. Okay. So these are just some important points that were included in the discussion, okay, from this study. One, that dematerialization increases environmental performance, okay, but is partially offset by internet energy use. Okay, as you've seen, no, mataas yung data center energy use and CO2 emissions. Okay, so that warranted sensitivity analysis. Okay, and the question was basically what parameters could flip the results. One is retail with zero customer transportation, transport emissions. So if you bike or walk to the store, okay, then you reduce the emissions and the energy use, okay, life cycle energy use by a lot. And then on one hand, if you need 5 hours, okay, to choose the album that you want to buy, then it could happen that that you actually have a higher footprint in terms of energy use and CO2 emissions. Okay, or if you prefer lossless files. Okay. And of course, there was also a discussion on suggested future work. Okay, so for example, customer usage patterns, are they different? Okay, other types of online music like single songs or subscription. Okay, and then energy use of streaming audio or video, like large upstream data, which entails large upstream data transfer. Okay, and this was done more than 15 years ago, I think. Okay, so now it becomes even more interesting, okay, with the heavy reliance of the world on the internet, no, all things digital. Okay, so we stop there for now. Okay, I will continue on the discussion on more specific energy related examples, okay, in the succeeding lecture.